Okay, so welcome back. In this one, we're going to expand and consider the bridge plus an N pedestrian crowd. Okay, so a couple of things to get out of the way first. One of the key assumptions that we said in this project was that there was no interaction between pedestrians, right? So we're not taking into account traffic effects. And there's also no human structure interaction. Now this, as we've already said, this greatly simplifies the simulation task because now we can rely on superposition. So to simulate the dynamic influence of a pedestrian crowd, all we really need to do is superimpose the response generated by N pedestrians walking individually across the bridge at different points in time. Now, because we're simulating a crowd, and one of the real features of a crowd is the variability between pedestrians, we're going to normally distribute our walking velocities. So we're going to generate walking velocities by sampling from that normal distribution that we talked about previously that was observed experimentally. Now, you could also randomize a whole range of different other features. You know, one of the other fairly obvious ones is body weight. You could look up what is the distribution of body weights for people, and you could put that into your simulation as well. Now, we won't bother doing that. But you get the idea. You'll see how we do it for walking velocities, so it's fairly easy to implement it for body weights if you want to. Now, one of the other reasons why we're focusing on walking speed is because it's directly related to pacing frequency, and that's one of the big things that's going to influence the dynamic response of your bridge. So our approach is really going to be to loop through each pedestrian, generate their ground reaction force. Remember, it's going to be slightly different for every pedestrian because they're going to have random walking velocities and therefore different/random ground reaction forces, and we're going to simulate the response of the structure due to each single individual pedestrian. So we're going to loop through them and get the response generated by each pedestrian. Now, bear in mind, they're going to be, shifted along the time axis at different points in time, because the other thing we're going to do is we're going to randomize the time during, the time that people arrive at the bridge, essentially, the time that people start walking across the bridge. Now, for simplicity, we're going to assume that arrival times onto the bridge are uniformly distributed within a window, right? So we're going to say there's a window of however long we like. We'll set it as a variable. So it could be a 10-minute window, a 30-minute window, 60-minute window, whatever you like. And we're going to say that people start walking across the bridge, or the times at which they start walking across the bridge are uniformly distributed within that window. Okay. Now, if you wanted to get a little bit more rigorous with this, you could come up with a Poisson distribution of arrival times. It's a fairly well recognized distribution that applies to arrival times, among other things. But we're just going to go for a uniform distribution of arrival times, just again a little bit for simplicity here. So we can get straight into it really and start defining some of the variables or constants for our simulation. So you'll notice again that I'm in a new notebook again. And again, you can keep everything in one notebook, but I've chosen to split things up for ease on my end. But what that means is I've got to bring in all the same stuff I had to bring into the last notebook. So we've got some parameters here, bringing in our Duhamel function, and I'm also bringing in our peaks function that we calculated or we constructed in the last lecture. So now down here, we're onto the new stuff. So what's the first thing we want to do? Well, we'd like to specify how many pedestrians are going to be in our simulation. Now, you can go wild here. You can go as many as you like. Bear in mind, the more pedestrians you have, the more time it's going to take for your simulation to run. So let's just I'm just going to stick with 100 here for now. The window, right? The simulation window, in terms of seconds, how long is it, right? So I'm just going to define window. Now, you can go as long as you like here, but I'm going to simulate a 30-minute window, which means it's going to be 30 times 60 seconds. So this is the simulation length in seconds, or the window length in seconds. Now, because a person might arrive, we're uniformly distributing arrival times, and someone might actually arrive at the very, very, very end of the window. But I kind of still want to give them time to walk across the bridge within our simulation. So I'm going to add on a buffer of additional seconds to just extend our window. And I'm just, again, this is kind of a figure a little bit out of the air. You could obviously play around with all these numbers and refine them if you like. But I'm basically adding 200 seconds on. So just in case someone arrives on the bridge at the very end of the simulation window, I'm going to let the simulation run on for another 200 seconds, which gives them time to cross the bridge and feature in our simulation. So now the mass of the pedestrian, we're going to go with a constant 80. You might choose to randomize that. That's up to you. Then the static weight of a pedestrian is 9.81 times MP. Okay. So that's our first round of simulation constants defined. All right, next we want to define the random variables. So those variables in our simulation that are drawn from a probability distribution. Okay, so we're going to start off with the start times. So we'll define a range of start times. And again, we're going to use NumPy here. So we're going to say from NumPy, we're going to call, from NumPy dot, we're going to call random. And then we're going to call uniform. Okay, so this is a function that NumPy gives us. We're going to pass in the lower limit. Our lower limit is going to be time t equal to 0. Our upper limit, let me say 0.0. Our upper limit is going to be, it's going to be window. Okay, and our size, how many samples do we want? Well, that's going to be 1 for every pedestrian, so it's n. Now I want my walking velocities, so I'll define capital V P as being, same idea, NP random, and this time I'm pulling from a normal distribution where the parameters I pass in are log, that's basically the mean. Okay, so that's going to be 1.3. Standard deviation is called scale. That's going to be 0.125. And again, the size is going to be 1 value for every pedestrian. All right then, so there's our random variables taken care of. All right, next step is to loop through each of these pedestrians and simulate the ground reaction force that they generate. Turn it into a modal force, apply it to the structure using our Duhamel function, and then save it. So save the force that was applied by the pedestrian and also save the response that was generated by the pedestrian. So that's the next step. So I'll start off by setting up a time vector for our simulation. So I'll just say T max is going to be equal to window plus buffer. So that's the total. This is the total time window for our full simulation. And then we're going to say time is going to be the usual way, np.a range. So it's going from 0 to T max plus del T. Okay, now we're going to initialize a couple of containers to hold our individual force and response values calculated for each pedestrian. So I'll define crowd force here as being equal to an array of zeros, right? np.zeros. Now, think about how we're going to store the crowd forces. I want to store the force for every single pedestrian, right? So individually. So for every, I'm going to save a force for each pedestrian on a new row within this 2D array of numbers, right? So how many rows do I need to have? Well, I need to have the number of rows matching the number of pedestrians in my simulation. And then how many columns do I need to have? Well, the number of columns needs to match the overall length of the time window. Okay, so we're going to have len and time here. And then we're going to use the exact same pattern to store the crowd response. So this is the response of the bridge, but we're not just calculating a single response. We're calculating an individual response generated by every single pedestrian. Obviously, they're going to be shifted along the time window depending on when the pedestrian started and how long it takes them to cross the bridge. Okay, now we can actually loop through each pedestrian. So let's just sort of emphasize that here by saying for each pedestrian. Right, so we're going to say for, we'll have a counter, we'll call it I. We'll refer to each pedestrian as n in, probably don't need I and n, that's duplicating. I leave it for now. Enumerate np.a range n. Right, so looping through each pedestrian, what do we have to do? The first thing we want to do is what's the pacing or the walking velocity for the current pedestrian? Well, we'll just take that straight out of the array of random values. So we'll index into the ith value. We'll say what's their start time? Again, indexing into the random array of start times. What is their crossing time? How long does it take them to cross? So it takes them, let me see, the span of the bridge, which was L, divided by their particular walking velocity, VP. And then what's the end time? What time do they leave the bridge at? So T end is equal to whatever time they started at plus their crossing time. Okay, now we can move on to start thinking about their force, the force that they generate. So what's their pacing frequency? Their pacing frequency was a function of their walking velocity, and so we saw that relationship previously. Let's drop it straight in here. So that was the polynomial that we talked about previously, referenced from the literature. Then the dynamic load factor Again, we saw that previously. That's a short one. I'll type that one in. 0.41 times FV minus 0.95. Okay, so now what we want is a time vector that corresponds to the pedestrian's time on the bridge, essentially, how long it takes them to cross the bridge. So let me see. I'm going to call this time vector. That's going to equal np.arange. Now this time vector, I'm just going to say it starts at 0. I'm going to shift it along the time axis in a separate operation, but we'll just assume it starts for now. It starts at 0. The length, it goes up to t cross plus del t, and it goes up in steps of del t. So that's the time vector. Let me generate a force vector off the back of that, a ground reaction force. Okay, so we're including the static and dynamic components of the ground reaction force. Okay, added in a few notes there. So now we're going to turn that force vector FV into a modal force for our bridge. So we'll do that in the usual way. So we'll start off by determining the position, right? So the position as a function of time was just the velocity of the pedestrian times the time vector. Okay, that's the position. Then the mode shape that corresponds to those positions was np.sine of pi xp over L. So pi times that xp we just calculated divided by the span of the bridge. And now we can say that the modal force was just going to be Fv times phi. Again, we've seen all this already. All right, now we're ready to actually calculate the response generated by this single pedestrian, right? So we'll say response is equal to Duhamel, and we're going to pass in time vector and Fn. All right, and then what we have to do is actually save this force. So we're going to save Fn, and we're going to save the response that was calculated, this guy. But remember, each of these pedestrians is starting at a different point in time, and so we need to identify the location within the overall data structure. In other words, we need to identify how far along that time vector we need to shift the modal force and the response for the given pedestrian, the pedestrian in question. So I'll say here we're saving the ground reaction force and response for this pedestrian at the correct position in the overall simulation records. So what that really means is we need to know what's the index that corresponds to this pedestrian's start time. So let's say I start, just a starting index, is going to be equal to whatever their start time was divided by del t. That should say divided by del t. Now, because that could give me a float, I'm going to say round it up because my index needs to be an integer, a round number. So that's going to be the starting index for this particular pedestrian. So we'll say index for start time. All right, now we have that, we can save into crowd force. So we'll say crowd force. Now, what row is it? It's going to be row I for the current pedestrian. And what columns are we saving into? We're starting at I start, and we're going from I start up to I start plus the length of Fn. Okay, and we're into that location, right? So this is an address within this data structure. Into that address, we're assigning in Fn. Okay. Now we do the exact same thing for the response that's generated by this pedestrian. So we can save into, within this different data structure, we're saving into the exact same address, and we're saying that's equal to response, and that's it. So that is it. Now, if you think about this, it's quite an inefficient way of coding this, because what we're doing is for each of our 100 pedestrians, we're coming in and we're calling this Duhamel integral 100 different times. An alternative way to do this would be to loop through each pedestrian, calculate the force, identify or save this crowd force, and then apply a single crowd force to the structure in a single call to our Duhamel function. Now you could do that. The way I'm doing it here is kind of, I think, slightly better from a demonstration point of view, because it preserves the individual force and response for every single pedestrian, but it's completely up to you. It would almost certainly be a lot quicker and more efficient to do it the other way. But again, this is really more about demonstration and learning than it is about coding up the most efficient simulation possible. All right, so let's go ahead and plot these forces and responses. Well, let's calculate them first and see if we've made any mistakes. Of course we did. Right, what's the issue? Could not broadcast input array from that to that. I see what's wrong. Up on line 3 here, well, this is definitely one of the things that's wrong. In generating my time vector, it is 0 up to that value in steps of that. Okay, so let's see if that's done it. Okay, excellent. Now, depending on the computer you're running on and depending on how many pedestrians you try to simulate, that might take a few seconds to run. If your code is taking quite a long time to run, well, then what I'd suggest is you reduce the number, either the number of pedestrians and or the simulation window length, okay, because that's going to really affect how long your simulation takes to run. So now that we've calculated all of these forces and responses, we can go ahead, as I said previously, and plot them. So we'll go for a subplot here. So same syntax that we used to generate subplots before. I'll generate 2 rows, 1 column. In the first row, I'm going to simulate, or visualize, I should say, the forces generated by each pedestrian. And in the second plot, I'm going to simulate the response, the corresponding response. So again, we're going to loop through again. Let me see, we're going to loop through for each of our pedestrians. So we'll say for I in, and we'll go np.arange, and I want to pass in the length of crowd force. So this is just going to give me a loop iteration for every row within crowd force. All right, so I can just say axes dot, no, not dot, indexing into the first set of axes. So axes 0 dot plot, and we're plotting time versus crowd force row I and all columns. Okay, that's fine. And then we'll go axes 1 dot plot time versus, let's go with the negative of the crowd response. And again, it's going to be I and all. And after that, it's just a matter of doing some housekeeping. So step out of the loop and add our housekeeping at the end. All right, so let's see what we have. Now again, this could take you a minute. Well, I don't know how long it's going to take you, but it probably won't be instantaneous if you've used or simulated a lot of pedestrians. Okay, so here we have it. So here's my my output. Now yours is going to look slightly different because we've used random start times and obviously velocities. So what you've got here is each one of these different colors is the modal load applied by a pedestrian within our simulation window. Again, time being along the horizontal axis. And then of course we have the individual response generated by each pedestrian. Now, in order to get the actual response of the structure, we need to superimpose all of these responses together. So that's the next step that we can do. We can actually superimpose all of these values, which is essentially adding up for every instant in time, adding up all of the force values that occur at that instant. And so there's obviously going to be some overlap between different ground reaction forces at the same instant in time. And we do the exact same thing for the displacement. Before I do that, I just want to demonstrate, like if I was to set a set of axes here, instead of setting my axes to be 0 and t max, my x-axis limits, if I came in here and I said, let's set the x-axis limits to be start time and start time plus t cross. What that would do is that would set the axis limits at whatever the last start time was and the last start time plus t cross. So what I'm essentially saying is, just for demonstration purposes, I'll set the axis limits based on the last person to cross the bridge. And we'll do the same thing down here. And we'll see that we get exactly what we had previously when we had just an individual person crossing. So if I was to comment that out, paste that in and run that again. Okay, so what you're seeing, this is interesting. What you're seeing is obviously this light blue record is the record that this start time and t cross is corresponding to, right? So this is the x-axis limits have been set based on this person here who's generated the light blue record. But what you can also see is there are other pedestrians contributing to the ground reaction, or to the modal load, I should say, which is obviously means they're contributing towards the modal response as well. And so if we were to generate the combined influence of all of the pedestrians within this window in time, for every time step we'd have to add up the values that occur at that time step. So for 1170 here, we'd have a contribution from the blue guy, from the red guy here, from the grey guy, and then 2 of these purple people here. And so that's what we're going to do next. We're going to cycle, well, we're not going to actually cycle through. It's going to be one line of code just to add up all of the rows within our crowd force and crowd response data structures. So let me just go back to and comment that out. Uncomment that and comment that out so we get the full simulation window again. So now let's sum up across the rows for the crowd force and the crowd response. So this time I'm going to define f crowd as being equal to the sum. So that's going to by default sum across the rows of, so essentially sum across each pedestrian crowd force. And we'll do the same thing. We'll say, let me see, that should have said res crowd response. All right, so this is going to give me the total modal load generated by my crowd and the corresponding total response, modal response at the mid-span location of the bridge generated by that crowd. Okay, next, before we visualize it, let's just extract the peaks. So we'll say peaks and times is equal to peaks, and we're going to pass in the overall response, mid-span response of the bridge for the full simulation window and the full time window. Okay, that's done, and now we can actually plot the modal loading induced by the crowd of pedestrians for the full simulation window, the modal response, and then the envelope of response. So that's what we're going to do next. So again, we'll go for 2 subplots here. So in the first axis 0, all I want to do is plot time versus f crowd, and then in the next window I'll plot time versus the response generated by that crowd, the negative res crowd, and then in that same second window I want to plot the envelope of response. So that's going to be times plural versus peaks, and let's plot that in a red line. Okay, and then let's add some axis labels and all the rest of it. All right, let's run that and see what we get. Okay, great. So here we have it. Now I didn't make reference to it, but I also added a vertical line here to the first plot and another vertical line to the first plot. So that's the first vertical line. That's the end of my simulation window. And then another 200 seconds on, we've got the actual end of the, or this was the end, yeah, that was the end of my main window, and then I added my buffer of 200 seconds to get the complete end of my simulation window. And it was just as well I did, because you still had people on the bridge walking off it after my simulation window had ended here, indicated by this first red line. So what we've got here is the, now let me see, a little bit untidy there. That should be force on that label in newtons. Go again. Okay, so what we've got here is the modal load, both the static and dynamic component applied by the crowd of pedestrians as they walk across the structure. So you can see as the traffic fluctuates on the bridge, we go through periods of relatively high loading. Here, for example, we've obviously got a lot of people on the bridge, and you could do another plot which plotted the number of people on the bridge versus time. That would be an interesting plot to have, let's say, some way overlaid on top of this plot. But what you would see is when you have a lot of people on the bridge, you have a large load, a large modal load, and then obviously there is one window here where there is nobody on the bridge, which is interesting. Another window here where there's nobody on the bridge. So again, this is the static and dynamic force. Now the other thing I noticed is I needed to plot the negative of my peaks. So let's try that. So that should be negative peaks. And let's go again. Excellent. So now this is the response, right? So this is the displacement of the bridge. So obviously you've got a very significant static component of displacement, but it's at too fine a level of detail here to see. You'd have to zoom in. But obviously what's going on here is you've got oscillations up and down, up and down, up and down. And so what would be interesting is to rerun this simulation and strip out the static component. Let's imagine you're not interested in the static deflection and it's only the dynamic component of the response you're interested in. And that's actually quite reasonable because if you're interested in the vibration serviceability of the bridge, you're not that interested in its overall deflection. What you're actually interested in is the acceleration that people are feeling as they walk across the bridge. And so you would strip out the static component of the deflection and you would just look at the dynamic component. So that would be the dynamic displacement. And then you would differentiate that numerically. So differentiate that record numerically once you've removed the static displacement. And that would give you the acceleration, the vertical acceleration of the bridge. And it's that value that you could then compare against acceleration limits or what you deem acceptable for your particular structure. All right, excellent. And so hopefully you can see that it's kind of handy. It's kind of nice having that displacement envelope as well. Okay, so that's more or less it. You now have a simulation that is going to allow you to simulate crowds of people moving across a structure. Now, as I've emphasized plenty of times now, we're just dealing with a simple footbridge here, simple linear structure, but you could just as easily map everything we've done onto a two-dimensional floor plate, provided that you have the mode shape for that floor plate, and that at any location you can identify the mode shape value and obviously the natural frequency, and all of this would map directly onto that. So that's worth looking at because you're probably you're probably more likely to be wanting to understand the response of a floor within a structure than a footbridge, a slightly more common use case. All right, so in the next lecture, we're going to look at building a visualization, a simulation of what's going on, an animation, I should say. So in terms of engineering data and information, you're done, right? You've got everything you need. These two plots here show you everything you need or provide you with everything you need to make a judgment on the acceptability of the structure. Now, there might be some further processing. Like I said, you'd probably differentiate this a couple of times, well, twice to get the acceleration and make your judgment based on acceleration. But you've all the information, the engineering information you need. So from this point forward, the next video, really all we're going to be doing is making ourselves a nice animation, something that is, it makes it easy to communicate to people what's actually happening. It makes it much more visual. So we'll pick that up in the next lecture.